This video is about efficiency in physics. Let's start with a discussion of machines. We define a machine in physics to be any device that tries to take energy in one form and redirect it or transform it into some new form. So I have three machines pictured here. We have a light bulb, a car, and a wind turbine or a windmill. In each of these machines, energy is put into the system or into the machine with the desire for a new form of energy to be put out. So for a light bulb, you put in electricity and you desire light to come out, electromagnetic energy to be the output. For a car, you put in gasoline, which has chemical potential energy, and your desire is that the car moves, mechanical energy comes out. For a windmill, the goal is to take the moving air, mechanical energy, and turn that into electrical energy, electricity. But hold on just a minute, machines are not perfect. Due to friction, air resistance, or other interference, some of the energy that gets put into a machine does not make it out as useful, desired energy. So machines are never perfect. A light bulb, when you try to light it up, it also produces unwanted heat. Cars, when you try to run the car, so much of the energy that you put in goes into just heating up the air around the car, or it turns into thermal energy. You run into air as you're driving, air resistance. So you end up losing some of that energy that you wanted. A windmill might experience some friction as well, or maybe some crosswinds in the other direction that interfere with the desired energy output of the windmill. So machines always turn a portion of their input energy into unwanted energy or thermal energy. And this is true for every machine. But I wonder, is there a way that we could try to see which machine designs are better than others? Which ones are better at taking the energy that gets put in and turning it into the useful energy that we want? Is there a way to kind of measure that? A way to measure the amount of useful energy that comes out of a machine is by the percentage that comes out versus how much you actually put in to the machine. So you can use this equation to find the percentage of useful energy coming out versus how much you put in. You just divide the two and you multiply by 100%. You can write this a little bit shorter this way. Efficiency is dimensionless, which means there are no units. It's just a percentage. It's a ratio of energy out versus energy in. And because of that, you can calculate efficiency using the energy output versus the energy input, or the power output versus the power input. Either way, you get the efficiency of the machine. So let's look at an example of that. Going back to our example of the wind-up toy car, you put in 10 joules of work at the beginning and the car has 10 joules of potential energy. That's the energy in to the car. But the useful energy that comes out of it is only 8 joules. 2 joules goes into thermal energy, heating up the air. So the ratio of output to input is 8 over 10. So the efficiency is 8 joules over 10 joules. So 8 over 10, that's going to be 0.8 times 100%. That's going to give us an efficiency of 80%. So I don't know if that's realistic for a car like this. I haven't actually measured this. But let's look at some more realistic examples of efficiency in common machines in our world. Now these are, I did my best to just do a quick little glance at some research here. So these numbers vary greatly for these different machines. So I'm just going to give you kind of a range for some of these, and based on different contexts and different scenarios, you might have better efficiency or worse efficiency. But for an internal combustion engine, that's what cars that run on gasoline are. Their efficiency is not great. It's usually between 20 and 40% efficiency. And that's because to make cars go, you have to burn a lot of gasoline. It creates a lot of heat. Whereas an electric car, they're much more efficient. They are somewhere around 90% efficiency. So they're much better at not wasting any energy, not turning a lot of that energy into heat. We have over here a coal power plant, or just like any kind of fossil fuel, burning a fossil fuel, turning it into electricity, where we get most of our energy, electrical energy, from where we are here. is an efficiency somewhere around 30 or 40%. And again, you have to burn it, and so it produces a lot of heat. That's why you don't get a lot of useful energy out of it, because you're doing your best to keep that heat into useful energy, but a lot of it escapes. A wind turbine usually has an efficiency somewhere between 40 and 50%. There's a lot of friction, a lot of limitations for how fast wind turbines can go before they break apart. So a lot of limitations there, 40 to 50%. It's a little bit more efficient. A solar panel, surprisingly, doesn't really convert a lot of the energy into electricity. And that's because it actually receives a lot of energy from the sun. If you think about how much energy comes into the sun, comes into the solar panel, it's packed with energy. Sunlight is packed with energy. It only converts 20% of that energy into actual electricity. So these efficiencies aren't a lot greater than the fossil fuel efficiency, but the difference between wind turbines and solar panels versus fossil fuel burning is that these are renewable. We can always get more wind and sun, but we can't always get more coal. So there's trade-offs for each of these. For an incandescent light bulb, these are not as common anymore, but these are the traditional light bulbs where you just basically are burning a little filament, producing light. They are very inefficient because they mostly produce heat and just a little bit of light compared to that. So it's only a 5% efficiency. That's why we don't usually use these a lot anymore. They're not very efficient. Typically we use fluorescent or LED lights now. I can't say that. Fluorescent lights are like the tube lights, and those have an efficiency between 20 and 30%. So it's much better, than the traditional incandescent light bulbs. And then a last one is a firearm. You shoot a gun. How efficient is it? Surprisingly, it creates a lot of extra heat and there's a lot of friction. So only 30% of the energy that gets put in actually comes out from the firearm. So those are some common efficiencies there. So that's all I've got for you in this video. Remember, this day could be your last, so live on purpose.